In this video, we'll add some more motivation for deep learning by discussing how flexible it is. We'll also see some tasks that can be addressed with deep learning that would be extremely hard to address for standard machine learning. So let's dive right in. Flexibility of deep learning. First of all, to highlight the flexibility of deep learning, let's remind ourselves about the design cycle of traditional machine learning methods and see how that relates to deep learning. So the first step in the machine learning pipeline was pre-processing. And this is actually not quite as important for deep learning because in deep learning, we actually operate on the original raw data. Then there's feature extraction and coding, selection, and machine learning. And all of these are actually basically subsumed by deep learning because, well, you actually learn the features and then you learn to select the right features in order to make the final classifier work as well as possible. And all of this is actually learned in an end-to-end fashion. So you basically only need to have this one deep learning system rather than different elements of the pipeline. Also, we have this end-to-end training. So we're replacing most of the machine learning pipeline by a single approach. And these different subsystems here are now all integrated in one. All of them are actually directly optimized using a single loss function. And we're learning the features that then work together well with the machine learning system. And by doing so, this is of course very flexible to apply to new problems because we only need to take care of this one system that we have and only maintain this rather than having three different systems. But most importantly, deep learning is flexible in terms of the tasks it can address, and that would be very hard to address with traditional machine learning methods. Of course, like traditional machine learning, it can address classification and regression tasks, and we've also already discussed that it can handle raw data as input very well. But it can also address structured output prediction tasks, where the form of the output could take the form of a vector, a graph, or image, or a sequence, etc. So some examples are as follows. In pixel-wise segmentation, which is also depicted here, we have an input image, and the output image tries to label each of the pixels of the input image with the appropriate class. Second example is machine translation, also depicted here, where we take an input sequence in one language and generate an output sequence in another language. The third example, parsing, is when you actually take a text as input and the output is actually a structured object, for example, a parse tree, whose nodes are verbs and nouns and adverbs, etc. The fourth example is image captioning, for which we also have an example here. There you take an image as an input, such as this one here, and then generate a caption for it, such as a young boy playing with a soccer ball in a field. And so that output is a sequence of words, a sentence. And the last example is denoising, also depicted here. So there you take, for example, a corrupted image, like this one, taken at night, and output a cleaned image that looks like a daylight version thereof. And you can do super resolution with these denoising approaches, and all of these tasks have actually already been successfully addressed using deep learning. And of course, they're just some examples of amongst many, many others. So the general picture would kind of look like this. We have inputs that can be all kinds of different formats of raw data, and the outputs could also be raw data or, well, structured data as well, sound and text and images and so on. And of course, also classification and regression. So all of these output modalities are possible. For example, for text to graph, what we just saw was a parse tree. From image to image, we just saw denoising and semantic segmentation. And when you think about this long enough for each of these input and output combinations, you could come up with some interesting applications. And if you have enough data, then you can typically also address these problems using a neural network. Interestingly, you can even have multiple input modalities at the same time. For example, you could have a video that also has sound. And then You could have one part of the network that handles the video, which is actually a sequence of images, and one part of the network that handles sound. And then at some layer of the network, these subnetworks could actually cross and exchange information. And if this happens early in the network, that's called early fusion. And if it happens late, it's called late fusion. That in the end, you could also think about having multiple output modalities. So you could, for example, generate a video with sound and closed captioning. So really the sky is the limit, and there's really this big flexibility of deep learning that is one set of methods that enable all kinds of different applications. So summarizing, one reason that deep learning is so powerful is that you can handle any type of input and output modality, and you just jointly optimize all the degrees of freedom with a joint loss function. And it doesn't really matter whether your outputs are sounds or images, or your inputs are sounds or images, as long as you can assess the quality of your outputs. And when you can assess the quality of your outputs, then you can measure that in a loss function, and you can optimize all the different combinations of the weights in order to optimize this quality, this loss function, directly over the entire network. So this brings us to the end of this video, and I'd like to leave you with these questions to think about for yourself. Thank you, and I'll see you in the next video.